All right, let's get started. Just so folks are aware who you're talking to right now. My name is Walton Shepard. I'm with the Natural Resources Defense Council here in Richmond, Virginia. I typically work on climate change related issues and decarbonization, typically in the power sector and transportation sector. But there's also the industrial sector, which is a significant driver of climate change, the embodied carbon and other pollutants that's involved in industrial processes. In this case, concrete. Some estimates show that concrete is responsible for up to 8% of global carbon pollution. That's global, not in Virginia. And one of the innovative ways to reduce the carbon and climate changing attributes of concrete production is through the state procurement process. As folks are aware, states are typically some of the largest purchasers of concrete, typically in the transportation space. So we're going to learn today about a method of tweaking the state's procurement process as a way of Virginia specifically, in this case, sort of taking a lead on saying, hey, look, we're purchasing a lot of this material. We want to do it in a way that's environmentally responsible and is a way for the concrete industry to sort of brag about its greening itself and making the product it produces more environmentally responsible, and a way of saying, hey, here in Virginia, we purchase concrete that has higher environmental attributes. We're going to hear from I'm going to turn it over in a moment, my fellow Richmond advocate with Open Air, Nikhil. He's going to manage the Q&A portion at the end, and he's going to in turn turn it over to Dr. Matthew Adams of New Jersey. New Jersey's a little bit further along in this lower carbon concrete space. So as we learn about this, if anyone has any questions as we're rolling along, feel free to, in the meantime, just plug them into the chat. We can have a more open discussion at the end, but if you want to just get a question off your chest in the meantime, plug it into the chat and Nikhil can manage those. With that, I will turn it over to Nikhil.
Good morning, everyone, and thanks, Walton, for the introduction. So I'm a volunteer for Open Air, which is a grassroots collective of volunteers working on things ranging from advocacy for low carbon concrete to building the first completely open source direct air capture machine. So we have no full-time staff, no investors, no board of directors, and no office, which I guess is no longer unusual in these times. We are not lobbyists and not representing any industry or companies. My co-presenter, Dr. Matt Adams, is a professor at the New Jersey Institute of Technology and is a technical advisor to Open Air. So as a personal introduction, as Walton mentioned, I'm a Richmonder. I've lived here for around 10 years. I used to work for a large financial institution in the area, but I'm transitioning to a career addressing climate change. In addition to Open Air, I'm a volunteer for the RVA Green 2050 Task Force, which is working to create an equitable climate action plan for the city of Richmond. So yeah, so that's, so the agenda for today. So I'll kick things off by setting the context on emissions from concrete and the policy proposal to address it through procurement. And then Professor Adams will go into depth into the technical aspects of concrete and the various types of low carbon concrete solutions. And we'll have a little bit of time for Q&A at the end. So before I go any further, I wanted to thank Walton and NRDC for their continued leadership on this issue and support to Open Air on this legislation in multiple states. So let's talk a little bit about the impact of concrete and climate. As you all know, concrete is everywhere. But what was surprising to me is that it's the second most used substance after water, and it's the most used man-made substance in the world. And concrete is here to stay. There are few alternatives that can match it for performance and easy availability and abundant availability of the raw materials that go into it. In addition, it is difficult to displace because it goes into structures like bridges and buildings and roads. So there's naturally a lot of risk aversion to adopting new materials. So it's pretty ingrained in the system. So the reason all of this matters is that concrete is a source of carbon emissions. I won't go into this in too much detail since Professor Adams will in the second half, but typically concrete is made up of air, sand, gravel, water, and Portland cement, which kind of acts like a glue to keep the whole mixture together. Portland cement, which is only about 10 to 15% of the entire mixture, however, accounts for 85% of the greenhouse gas, about 85% of the greenhouse gas emissions in the manufacture of concrete. And you can see here that it's a major problem. It's about 7% of the share of global CO2 emissions. And here, this just shows the parts of the cement manufacturing process where carbon emissions are highest. You can see that the calcination process right at the center accounts for really a majority of the carbon emissions. And there are two types of emissions here associated with this step. The thermal emissions, which you see where, because this is a very high temperature process, the temperature goes up to, we have to heat up the kiln to about 1400 degrees Celsius. So that's results in a lot of carbon emissions. And there are people working on addressing it, but as you can see, that's not enough because the process itself, the calcination, results in more emissions because the calcination process actually results in the calcination of limestone, results in the release of carbon dioxide. So the problem is clear, but is there a policy approach that can work to address concrete emissions? In the Virginia context, as Walton mentioned, this is important because it will complement the significant work that has begun to decarbonize other sectors ranging from the power sector to transportation. We need to start looking at the industrial sector, which accounts for approximately 10% of the state's emissions. And this is an attempt just to do that. So we started looking at ways to tackle this problem through legislation. We soon zeroed in on state governments because they are usually a major procurer of concrete for public works projects in most states. In addition, states can play an early adopter and market catalyst role, just helping to bring down the cost of these often innovative new materials so that it can be more widely adopted in the industry. So we looked for some policy legislations that we could get inspiration from, and we found several examples at different levels, from local jurisdictions to all the way up to countries like Netherlands. So California's Buy Clean program is often a gold standard for climate-based purchasing requirements, although it does not address concrete yet. The Port Authority of New York and New Jersey has been requiring low-carbon concrete since the 1990s. And we talked to them, and recently they have seen reductions in carbon emissions of up to 30% with no additional costs. So that kind of gave us confidence that we can do this and not have, like with existing materials, and not have significant cost impacts in government. And that's always important. The city of Portland, Oregon has a low carbon concrete procurement program, as does the country of Netherlands, which has had it for over 10 years and has used it for $1 billion of low carbon concrete procurement. In fact, the Netherlands policy is very similar to the policy proposal that we'll talk about in the next few slides. So with these examples, it felt natural that we focus on state and local governments. Our first LECLA bills, which stands for the Low Embodied Carbon Concrete Leadership Act, was first introduced in New York in 2020, and a modified version of that bill just passed in the 2021 session. The New Jersey version of LECLA was introduced a few months ago and will be up for voting in the fall legislative session. So we think Virginia, with all the momentum on climate legislation, can be the next state to pass LECLA. How does LECLA work? We call the mechanism for incorporating climate-related considerations into the bidding process climate competition. What this means is that bidders still have an incentive to provide the most competitive pricing, but there's an additional incentive to improve the climate properties of the material. The key artifact that determines the climate properties of the material is the EPD, or the Environmental Product Declaration, which LECLA requires. So the EPD is, as you can see, it looks like a nutrition label, and it's an industry standard life cycle assessment tool that quantifies the environmental performance of materials across the entire production process. It measures the indicators per cubic meter of concrete. And you can see here the global warming potential. That's one of the indicators in the EPD. It measures the CO2 emissions associated with the production of the material. The good thing about the EPD,
sorry, Nikhil, just to be clear, when you say bidders, you're referring to concrete suppliers making bids to the state to purchase the concrete. Just want to make sure that was clear to folks.
So more generally, the EPD is gives you the global warming potential of the material, of the final material that's being purchased. So the good thing about the EPD is that it's now an industry standard life cycle tool, as I mentioned, and if concrete companies submit certified EPDs for their mixes, we can make apples to apples comparisons of their global warming potential numbers, and they've been extensively used in various jurisdictions. So that's the good news here. So the bill itself has two components. One is the bid advantage for low emissions, which we'll go into with an example, and a tax incentive for creating EPDs, which is a useful tool for those who are doing it for the first time. So let's just go over the bidding process with an example. LECLA provides a maximum discount of 5% for the bid with the lowest global warming potential. So say we have a project that gets 4 bids and they all submit their EPDs. The bid here, you see bid 1 has the lowest global warming potential. And if their bid comes in, so if they bid for the job for $100, the 5% discount means that the bid would be treated like it was for $95. So immediately they get that advantage in the bidding process. The other bids will also get discounts. They could be they'd probably get they'd get a smaller discount, and this could be on a sliding scale. There could also be a global warming potential threshold that ensures that bids with high GWP scores don't get a discount. So in this example, a threshold of 400 means that bid 4 wouldn't get a discount. You can say the thing with the LECLA is that there's a lot of flexibility in this, and your discounts can change over time to incorporate more innovative materials. And so is the threshold. You could start off without a threshold, or with a high enough threshold to ensure that you're getting like maybe not as advanced technology in to begin with, but things will become cleaner and cleaner concrete as things go on. So the competition aspect of LECLA is that the bidders don't know each other's bids, just like in an ordinary bidding process. So they're still incentivized to submit a low bid, and that helps keep costs low for governments. So and climate competition rewards bids that give the most climate benefits for the lowest cost. As I mentioned, the final component of the bill is a tax credit to help concrete producers pay for EPDs for their concrete mixes. This has been done effectively in places like Portland. Just to summarize, or just a few key points on the obligations, all departments, agencies, and public institutions under the state would be obliged to go through this process. However, there's a limit of 50 plus cubic yards, just to make sure it doesn't result in onerous legislation or regulation for really small jobs. So it eliminates jobs that are the size of single-family homes, typically. And the obligation is transferred to general contractors who subcontract out for the bids. Some advantages of LECLA. One, it's technology agnostic and performance-based. So it allows for concrete producers to combine multiple solutions. Some of the solutions that Professor Adams will talk about can be combined together. For example, they could substitute for the Portland cement with materials like fly ash or ground glass pozzolan. And they could also do use breakthrough technologies like carbon capture and storage. It rewards innovation by having a flexible discount mechanism that can adjust as new technologies come to market. It has no mandates, so it does not even require that concrete producers provide EPDs, and it maintains the cost benefits of competitive bidding. So some of the groups that support the bill nationally and in the states that it has been introduced, NRDC, of course. This you can see includes architecture, organizations, infrastructure, engineering, policy think tanks, and environmental organizations. So yeah, I wanted to thank you all for the time and for the interest in addressing concrete emissions. We believe that this is a pragmatic approach that will work in Virginia and would love your help in getting a bill to pass next year. So please reach out to me for any suggestions, or even better, join our team at openaircollective.cc. I'll also put my email in the chat. Thank you.
Hey, Nikhil, if I can jump in before you turn it over to Dr. Adams, I just want to make it clear, if you would, sort of where the rubber meets the road of how this functions. If I'm the lowest embodied carbon concrete supplier, my bid gets am I correct that my bid at the state level, they see the certification that yep, this guy is providing the lowest carbon concrete. His bid gets a 5% discount. So his bid appears to the state to be 5% lower. So that bidder has that 5% reduction in the bid, the appearance of the bid price, even though the state doesn't actually pay that 5% discount. As far as the selection process, that's how it actually functions. Is that correct?
That's correct. So in that example, the bid was at 100, but the state would see it at 95, but would actually pay 100 if that bid were successful. Yeah. So yeah, as I turn it over to Professor Adams, I'd just like to briefly introduce him. Dr. Adams is an expert in the chemistry and durability performance of cementitious systems for use in infrastructure. He joined New Jersey Institute of Technology as an assistant professor of civil engineering in September of 2015 after completing his master's and PhD at Oregon State University. So prior to graduate school. He worked as a structural design consultant in Boston for several years. So he's very familiar with the industry, in addition to being an expert in low carbon concrete. So take it away, Professor Adams.
Thank you very much, Nikhil, and thank you everybody for coming today. So as Nikhil said, I'm an assistant professor in the Department of Civil and Environmental Engineering at the New Jersey Institute of Technology. And here I am co-director of the Materials and Structures Laboratory, where we study sustainability and durability of concrete materials. So we're looking at how we can work with existing and new technologies to improve our concrete, make it more sustainable, but also make it last longer and meet the requirements that it actually needs to meet. So, you know, one of the key things, and I'll talk about this throughout the slide, is that stronger concrete is not always better. Stronger concrete means more cement, which means more carbon, embodied carbon. We don't always need the strongest system. So there are lots of different concrete mixtures out there that work for what we need them to, yet also we can use them to reduce the overall embodied carbon. So before we get into all of those solutions, I just want to put us all on the same page of what is concrete, how does it work? And I like to use the cookie metaphor. Concrete is a lot like a cookie. So in a standard chocolate chip cookie, you've got eggs, flour, and butter, and this is your glue or binder material. You have sugar and chocolate chips. This is your filler and flavor. And then you have baking powder, baking soda, and salt, and these are sort of your modifiers. If we look at concrete, we have similar components. We've got cement and water that act like your glue and your binder, sand and gravel, which is your filler material, and then we have chemical admixtures which can modify some of the properties of the concrete. And just like a cookie, you have your standard basic chocolate chip cookie, but there are many, many varieties of cookies out there where you change the different components to get your desired effects, right? Maybe you really like peanut butter, so you add peanut butter into your cookie, and that's going to change your cookie around. It's still a cookie, it's still meeting the same basic idea of a cookie, but you've modified it to what you want. The same thing is true for concrete. Your basic concrete mixture contains some air, hydraulic cement, which is mostly Portland cement, or most usually Portland cement, water, and aggregates. The aggregates is our sand and gravel. Those fill up most of the space in our concrete. But you know, we can also exchange those. We have alternatives to the cement. We can put in recycled aggregates or waste material aggregates. And then we have a lot of these chemical admixtures which can speed up the hardening process, slow down the hardening process, make it more fluid, make it more resistant to colder temperatures, things like that. And so there's a lot of different alternatives to this basic mixture. And included in this is where we get green concrete. Your basic concrete mixture is not terribly sustainable, but we can add in some of these alternatives to reduce the embodied carbon and get us to a much greener or environmentally friendly concrete. So as it was mentioned earlier, concrete's responsible for about 8% of the total CO2 output worldwide. And sorry, that 2 should be a subscript, not a superscript. But yes, there's a lot, it is responsible for a lot of the CO2 output worldwide. But there's always this question, why? You know, it's good to look into this number. This number sounds really large, and it is, but there's a reason why. Concrete is produced at a massive scale. It is, as Nikhil said, it's the second most used material in the world after water. It is the most used man-made material in the world. We pour almost 2 cubic yards per person per year in the entire world, which is, you know, that is a lot. This cube here is about 1 cubic yard. You can see my friend sitting on top of it. That's a lot of concrete. If we look at concrete and its embodied carbon on a per unit scale, so for every kilogram of concrete, it actually has a relatively low embodied carbon compared to other building materials. So it's lower than brick, timber, plywood, and much lower than steel. But we make so much of it that we sort of overwhelm how much carbon is being produced by those other materials because of how much we make. And so this is still important. Even, concrete is not going away. There is no real alternative to it in the foreseeable future. There's nothing coming down the pipeline that's going to replace it that performs better or is more environmentally friendly. But we can do a lot of things to reduce the overall embodied carbon. So to understand what those are, we first need to figure out where all of that carbon is coming from. Most of it is actually coming from the cement. The cement production is the source of most of that embodied carbon. And we can break the cement production up into three main areas. You have the quarrying, transport, and grinding of the raw materials. That's about 10% of the overall embodied carbon of cement. We have what are known as thermal emissions, and that's 40% of the embodied carbon, and then process emissions, and that's 50+% of the total embodied carbon. And so we'll talk about what all these different types of emissions are. So when we make cement, we make it in a rotating kiln. It's about the length of a football field. It's very big. You can stand up inside of this kiln. It's a very big system. And we introduce ground up clay and limestone at the top of the kiln. It's set at an angle and it rotates. And so the material slowly slides down to the bottom of the kiln. At the bottom of the kiln, we have a flame and hot air is being introduced. And by the bottom of the kiln, the material reaches about 1400 degrees Celsius or about 2500 degrees Fahrenheit. So the material gets quite hot. So as part of this process, though, we have to heat it up. So we have a fuel source here where we need to heat that material up. The most common fuel source is coal, but we do use oil and gas. We also use waste materials like tire rubber, biomass, and some wood as well. And so, of course, this is a major source of CO2 when making cement. We have to burn all of that. That releases carbon into the atmosphere. But that's actually the smaller of the two main cement, CO2 production things in cement production. This is our thermal source. This is about 40% of the overall CO2. Where the majority of the CO2 comes from is from this process known as calcination. We need limestone in our concrete, in our cement, because we need to break that down and get calcium oxide. This is a very important chemical component to the process. So limestone is CaCO3 or calcium carbonate. When you heat it up, it breaks down into calcium oxide and carbon dioxide. And that release of carbon dioxide is where actually 50% or more of the total carbon that is produced during cement production comes from. And so even if we were able to switch to completely renewable resources that had no carbon output to heat up the kiln, we would still release a major amount of carbon because of this breakdown of limestone. And there's really no other way to get that calcium oxide in a cost-effective and abundant manner. Limestone is everywhere. It's easy for us to break down. We're not going to change this process anytime soon. So, and then the other 10% of our total emissions comes from the mining of the raw materials, grinding of the cement, mining of the aggregates, and the transportation, but that's relatively small. Most of this is coming from the actual cement production. So how can we reduce the embodied carbon? Okay, so if we know that most of the CO2 is coming from the cement, we can think about reducing that portion of the concrete that is made from hydraulic cement. So we reduce the total amount of Portland cement that we're putting into the mixture. Fortunately, there are a lot of options out there. Portland cement, which is the process that I described a few slides ago, is the most common of the binder materials that are out there. It's around 90% of the market. Most of the concrete that you walk on, that you live in, work in, is made with Portland cement. We have other types of hydraulic cements that behave similarly, such as calcium aluminate cements and calcium sulfoaluminate cements. These do have slightly lower carbon footprints, but they also have very niche applications and they're more expensive. And then we have things like magnesium phosphate cement and geopolymer cements. So we don't use these quite as much. Why are these really only about 10% of the market? They do have a lower carbon footprint, but with the calcium aluminate cements and the sulfoaluminate cements, they are about 5 times as expensive as Portland cement. They are widely used, but they're really made for specific uses. They're not as easy to work with. They are not necessarily as durable in all the same situations as Portland cement is. And so, it's not something that we are going to see being used as a full replacement. Something like magnesium phosphate cement, this is a really interesting replacement, but the idea of trying to replace all of our Portland cement with magnesium phosphate cement sort of ends with the fact that there isn't really enough phosphorus material available for us to replace that. And we really need the phosphates for fertilizers. And so there's just no possible way for us to replace the amount of Portland cement we make with this. Geopolymer cements, these are really interesting things that use some waste materials, but they are limited in availability and they require special training to use, and they're not quite there from a technical aspect yet. So, these are things that might be coming up, but again, they're not going to replace Portland cement anytime soon. What we can do is use something other than a hydraulic cement. So if we think about our total cement content as our cementitious materials, rather than it having to be all hydraulic cement, we replace some of that Portland cement with these other materials called supplementary cementitious materials. And so we can actually grind up limestone and put that into the mixture. We use common ones like fly ash, slag, silica fume. These are all byproducts of other industries. And then we have newer ones coming out like ground glass pozzolan. Ground glass pozzolan is produced from waste glass. It's ground up. Calcined clays are just clays that have been heated up and crushed down. The great thing about these is that they typically have a moderate cost. So they're not, you're not really increasing the cost of your concrete. And most of these are already heavily in use. Most of these products are actually going to improve the durability, help improve the strength, and they've been being used for years to do that. And now, it's just a mindset shift of, okay, these can also be used to help increase the sustainability of our systems. So some background on some of these materials: ground limestone. We make what we call PLC cement, or Portland limestone cement, and this comes to us directly from the cement plant, where around 12% of the cement is actually limestone. There's no impact on strength or durability. It's a very good product. There is some availability in the US, but it's not sort of generally available. You generally have to special request it, but that is changing as the demand increases, and it's been used very effectively in many different applications. And so, those are really good options. Those SCMs are really good options for reducing our cement content. The other thing we can think about is reducing our total cement content through our mixture design. So if we think about concrete as a particle packing problem, so how much of different particles can we fit in there with as little void space as possible, if you can make all of your aggregates of the right sizes, you can reduce the amount of space in between them. Cement fills up the space between the aggregates. And so it basically binds them all together. So if we can increase the packing of our aggregates in the concrete, we reduce the amount of cement that we need. This is still a new technology that is being developed on how to do this best. It's not available everywhere. You need to work with the aggregate supplier to really understand if they have the capabilities to do this. But you can reduce up to like 30% of your cement content just by changing your aggregates, and you see no real strength or durability change, though it does increase the cost of your aggregates right now, because this is something that your aggregate facility would need to spend time figuring out how to do, probably change their process. So right now there is a bit of a increase in cost in this. The next idea for reducing the carbon in concrete, this is more on the up and coming side of things, is incorporating carbon dioxide directly into your mixture. So there's a couple of companies out there that have proprietary systems for doing this. A big one is Carbon Cure. Basically, you put about 1% by mass of your cement in as CO2. So if you have 100 pounds of cement, you're putting in 1 pound of CO2 into the mixture. That CO2 is actually going to help increase the overall strength, which means that you can reduce your cement content. And so the real benefit from CO2 is not only from inputting CO2 in there, but it lets you reduce your cement content. And anything that lets us reduce our cement content is going to have a big impact on the embodied carbon in our concrete. There's other companies like Solidia Technologies working on similar ideas. This is not widely available yet. It's coming. It's, they're working as quickly as they can with different cement plants and producers to get this out there. But this is where something like this procurement bill can help sort of push these technologies forward to try to get them into the marketplace quicker. So if we move away from the cement, we can do some things with the aggregates using alternative aggregates. These have less of an impact because there's overall less CO2 produced from producing the aggregates. But we can replace some of our natural aggregates with things like recycled concrete aggregates. These are low cost, widely available. You can easily replace up to about 50% of your concrete. The difficulty with them is that they can be inconsistent in quality, so you need to work with an aggregate producer or a recycled concrete supplier that knows what they're doing and is doing good quality control of their system. But the real benefit in CO2 here is that particularly in urban areas where you may have used up most of your good quality aggregates close to a city, using the waste aggregate is going to reduce the overall transportation costs and reduce landfilling, which is going to reduce CO2. We also have things like glass aggregates. Those are limited in availability and not good for all situations because there's some durability concerns. And newer technologies moving forward are these manufactured mineralized carbon aggregates. And these are really interesting. A great promise for carbon capture, where they actually take CO2 and mix it with calcium and deposit this fake calcium carbonate around the aggregate and basically make a manufactured limestone on the aggregate with captured CO2. And so this has some really interesting promise. There's a couple of companies doing similar technologies here, but they're not really available widely yet. But again, this is new technologies that are coming down the line and hopefully will be more available soon. One of our best options, though, if we're not interested in changing our materials right away is designing for durability. The longer we can make our concrete last, the less likely we need to replace it. And every time you replace it or repair it, you have a new set of embodied carbon for those materials. And so, the standard practice for many years has been to design your concrete for day one, not necessarily to design your concrete for 50 years, 100 years down the line. And so making sure that our design specifications have us looking at not just the strength for day one, but how long is this concrete going to last, and ensuring that it's going to last for quite a long time is going to reduce your need to replace concrete, which will have a big impact on our CO2. And then another thing to keep in mind is don't over design. We often make concrete that is much higher strength than it needs to be. If you only need 4,000 pounds per square inch of strength for your concrete for the structural specifications, then don't order concrete that's going to get 8,000 pounds per square inch of strength, right? That means more cement content. And so more cement content is more CO2. Not everything we build is the Burj Khalifa, right? We're not building mile-high buildings everywhere. We don't need that high strength of cement for most of our applications. So get the concrete that you need rather than overshooting those boundaries. And that's also going to keep down your embodied carbon. So in summary, there are lots of ways to reduce your embodied carbon. I often get asked the question of, what is low carbon concrete? Can I just go and buy low carbon concrete? This isn't a product that you get off of the shelf. There are many, many, many different ways to reduce the embodied carbon in concrete compared to a standard system that has all Portland cement in it. The good thing is there are lots of them that are already being extensively used in construction. We're just not thinking of them as low carbon mixtures. And once we do, then we can get to the next step and make them even better. There's a lot of exciting technologies on the horizon that we need to make sure that we're fostering and bringing into the marketplace. These changes can be done pretty quickly and easily. Generally, your concrete plants will all have something available that will meet low embodied carbon, even if they don't know it. Like most concrete plants are working with some type of supplementary cementing material. But the key is making sure that you have good communication between your engineers, your contractors, and the people that are procuring the concrete, the state or the towns that are procuring it. Making sure that everybody is on board with this being a design specification for the project, right? It's not just strength, it's not just durability, but also including embodied carbon or sustainability as one of the design objectives will help everybody work and get there quicker and on task. So that's it. Thank you for taking the time to listen to me, and I'll be checking the Q&A for any questions.
Yeah.
Yep.
And so we'll.
Go ahead, Walt.
Oh yeah, we'll transition to the Q&A. I believe in the written format for now, because I think folks are muted. But if anyone has a burning comment to make, maybe we can unmute. But for now, we'll do the written. And just to synopsize what I heard, it's basically, the solutions are out there, and some are still gestating and improving. Some are already there and proven. LECLA is essentially a cue to concrete providers to say, hey, you can in effect get a premium if you incorporate some of these improvements. By the way, as a reminder, on a totally voluntary basis, right? LECLA is just a voluntary option to providers to maybe get that discount in the bidding process if they incorporate it through the LPD sort of disclosure. One of the questions did sort of mention more locally here in Virginia, right? Like concrete suppliers are local. You know, they are local providers. You have local bidders because you can't transport concrete feasibly over long distance. There are, as I understand, also cement, Portland cement supply, at least one in Virginia, as I understand. So, you know, this is like a local, real thing for local providers to take part in. And one last thing I'll flag for Dr. Adams or anyone else to chime in on is coal ash as a potential lower carbon material substitute to reduce the overall content. As folks may be aware, in Virginia, we do have a lot of coal ash lying around, and we are very much in the process of starting to deal with and process and reduce the environmental presence of coal ash in Virginia. So those are just some of the real sort of opportunities we have inside the confines of our state. So I just wanted to flag those as potential real solutions locally.
Yeah, I just want to bring up the fly ash question, and Joan, I see you ask a similar question in the chat, and I'll just sort of try to answer it here. You know, fly ash is sometimes considered problematic because it's a byproduct of coal burning. And, you know, in the concrete industry, we are certainly not advocating that we burn coal for the sake of making fly ash. There are alternatives to fly ash out there as an SCM, but the reality is that coal is being burned and fly ash is being produced. And better to put it in concrete than put it into waste landfills or slurry pits where it can cause more damage. When we put the fly ash into concrete, we actually immobilize it, and so it becomes much less damaging to the environment. And so, you know, this fly ash has been used for many years in concrete very successfully. And we have a lot of research going on in ways to make the fly ash that maybe wasn't good enough for use in concrete 20 years ago better so that we can use it today. So not only are we able to use what's coming out of coal plants now, but we're working on getting the fly ash that is in landfills and in slurry pits and making it so that it can be used in concrete. So this use of SCM is not just using up a waste material from current coal burning, but from past coal burning as well. And so, you know, there are some folks that have suggested that we not allow the use of fly ash, but in reality, being pragmatic about the fact that we can use this technology to remove fly ash that's currently waste material is a real goal for us.
Great. I think Joan had another question on how do you get developers, that Professor Adams, probably you can answer on how do you get developers to plan for their projects to last 50 to 100 years, as you had mentioned, that there's no substitute for more durable projects.
Right. So, you know, the upfront cost for more durable systems can be a little bit more, but working from a life cycle cost approach is the best way to work with this. Of course, you know, when it comes to private contractors, you know, the best you can do is encourage them to do so right now. But when it comes to the state, you know, these sorts of procurement initiatives can help to push those ideas forward. You know, and anybody that is in the audience here that is an owner, you know, that's the person out there purchasing concrete or purchasing these materials, you know, you can set up with your designers that you want this to be a goal of in your specifications, and you require your concrete manufacturers to meet these goals. And so the technology and the concepts are out there. It's just a matter of having the owners really interested in it, which is a difficult task. I agree with that, Joan.
Great.
Chris, yeah, there was a question in the chat, which I'm trying to pull up from Laura about the groups that are opposed to the California Buy Clean Act, or more generally to these legislations. So, Chris, with your experience, would you like to answer that question?
Yeah, I can try. Again, I'm Chris Neidl. I've been working a lot on the LECLA legislation for the last couple of years in New York State. We also have, I see on the call, some of the activists that are pushing it forward in New Jersey. And I think there's no one answer to that question. It really depends on the policy and it depends on the place, right? So California, even compared to New York, is a kind of a universal way in terms of what conditions sort of prevail there. You know, there's a lot. It's one of the largest cement manufacturing states. Buy Clean is a bit different. That covers all these different building materials except for cement and concrete, which were excluded right at the end. And there are folks trying to get that included right now. So in general, it really varies who opposes the bill. And it's really also a function of how well the bill is understood. I think that that's been the key lesson learned in New York and New Jersey, is that it's any new subject like this that's, you know, involves a policy that's new, is bound to be, you know, sort of mistaken. So there's a lot of education that has to get done. And I think we made really good progress with that in New York and New Jersey. Certainly you'll have folks from the contracting and construction community that, you know, will maybe look with some skepticism at policies like this because it changes the status quo. You know, same from producers, concrete producers. You know, we believe that in the spectrum of policy options, LECLA's core incentive basis, the discount basis, empowers concrete producers to sort of decide which options are best for them. It really puts the ball in their court. So we think it's really about as sympathetic to the concrete producer as possible, but you got to do some education there and you got to engage early. So I'm happy we have some folks on the call from that world. Would love to talk to you. And then just to close, there is a real committed activism on the local level from folks that live close to cement kilns, you know, that have real concerns about air quality and water quality. And there's a real history there of, you know, being suffering, you know, damage. And so there's understandably, when folks see a bill like this, sometimes they don't make the distinctions between concrete and cement, and they see the word incentive and it can be construed as something that's sort of for industry, which, you know, it's not. It's for climate that acknowledges that industry has to be your partner in reaching the proper solution. So that also requires a lot of input early and a lot of conversation, I think, with those communities that are impacted or closely proximate to cement companies. So hopefully that starts to answer the question.
Thanks, Chris. If there are any other questions, should we like unmute to see if there?
We could
unmute the audience. Yeah.
Let me see. There's certainly good comments in the chat, I would see. I'm just trying to see if there's another question. You know, it is interesting. I see Lori, who's in North Carolina, an activist based there, very similar issues around fly ash, coal ash, where do we put it, that are really prominent in North Carolina. So what I think is just a kind of a theme here is that as Virginia sort of pursues this, and there's other states that are also looking at it, having a conversation across states about which sort of conditions apply, I think is really important. And it's good to see that is already sort of happening. I'm not sure if anybody wants to, if you have a question, I would say, even if you put it in the chat, if you can go ahead and put it in the Q&A, a question or a comment, and we could speak to it, or if there's a brief comment that you would like to make that's related to the subject, I could certainly give you permission to talk. Great. Nikhil, I think, you know, we had booked an hour and a half on this just to give ourselves sort of a buffer, but I think we would probably land on an hour, which is where we are right now. I do see this question, which I like, from Joan, which I was actually going to, if you see it in the chat, Nikhil, you know, well, it's the question that I answered about local projects. You know, I think that this is confined to state projects. But what we're seeing in places like New York, certainly, and in New Jersey, there's a real relationship between local jurisdictions and what they're deciding to do in the state. And it can work in both ways. We have a couple really progressive climate progressive, climate active communities in New York State that are already starting to implement resolutions of support and do pilot projects around procurement, around low carbon concrete. And when we have those local examples that we can point to in our advocacy on the state level, that influence can really bubble up, right? But certainly if you have the state comes in and implements, is one of the largest purchasers of concrete, what they do has a reverberating impact down to more local levels of government as well. So if you have the state come in with an EPD or other life cycle based analysis program that also includes a tax credit, that's going to ensure that more local providers that also provide to local governments will now have that capability to produce EPDs, which then means that local governments, after a certain period of time, might be able to just assume that they can request EPDs for their own bidding. So there's a good dynamic, I would say, between local, and we shouldn't discount the local. I mean, local can move fast. There's a lot of creativity, and so they can be super influential. So if you're interested in that, we will follow up after this. But Nikhil, I want to really thank Nikhil for really getting this going in Virginia. He's been sort of working this as a volunteer for several months, and certainly the leadership of NRDC nationally and in key states has been really critical. Nikhil, did you want to say anything about what we're sort of looking at as next steps maybe in Virginia?
Yeah, so next steps really are, we want to start firming up the legislation, getting this out in front of lawmakers and trying to gin up support, educate people, as you said, Chris. It's important to reach out to all the stakeholders and make sure they understand the legislation and that it is really to kind of build a market for clean concrete, low carbon concrete. So so the question about what can Virginia residents do to help is there are a number of things, both including reaching out to lawmakers, finding local and other stakeholders that we need to talk to. So please reach out to me or either at the Open Air website, or I'll actually include my email here in the chat as well.
Yeah, what I would even say from a more global perspective, the person who just anonymously asked that question, what can we do to help? What we've seen in other states, you've got Sue and Sean and other people from New Jersey on the call, some of the folks from New York, is that this really gets driven by grassroots activism in partnership with subject experts and real, established advocates like NRDC. So Nikhil and a couple of other folks have really started to get the momentum going around this from the grassroots. If you're interested in participating or joining a small group to help get this going, legislator outreach, coalition building, Nikhil just put his email there. This only works if there's participation from Virginians. So please do reach out to Nikhil, and we'll bring you into the fold and let you know what ways you can participate. But it's critically important. Great.
All right.
Nikhil, anything else? I think that was excellent.
That's it.
Thanks, guys.
Thank you, everyone.
Thank you, everyone.
Have a good weekend.